In this video, we're going to look at using moles, which are the chemist's counting group, and to relate moles to mass of a sample, and to relate moles to number of atoms in a sample. Now, the mole, the chemist's counting group, is necessary because atoms and molecules are obviously too small to manipulate in any sort of reasonable way in a laboratory. And because they're really small, any counting group I have, something like a dozen or a 24 pack, is not going to be enough. I need a very, very large number to have a measurable, laboratory handleable quantity of atoms or molecules. And the number we've hit on is 6.022 times 10 to the 23rd. So a mole of atoms would contain 6.022 times 10 to the 23rd atoms. The reason I need a number so big is to get a reasonable sample because atoms and molecules are so very small. Now let's look at how we would relate the mass to the number of moles. And I do that on an element by element basis using the periodic table. The periodic table contains information on the mass per mole of each element. The entry for carbon, you see that bottom number, 12.011. That's simply the number of grams in each mole of carbon atoms. So 12.011 grams of carbon would contain 6.022 times 10 to the 23rd atoms. 1 mole of hydrogen contains 1.008 grams of hydrogen atoms. And oxygen, 15.9994 grams in each mole of oxygen atoms. Now let's proceed to calculate a molar mass. And the example we're going to use is benzoic acid, which has the formula C7H6O2. And I can tell from this formula that each mole of benzoic acid must have 7 moles of carbon, 6 moles of hydrogen, and 2 moles of oxygen. So to get the molar mass of benzoic acid, I simply add up the mass of all the moles of the elements that are present. So I'll start with carbon. The contribution to the molar mass of benzoic acid from carbon is my 7 moles of carbon times the 12.011 grams in each mole of carbon from the periodic table. That gives me 84.00077 grams of carbon in my 1 mole of benzoic acid. Same for hydrogen. We'll take our 6 moles of hydrogen times the 1.008 grams in each mole of hydrogen from the periodic table equals 6.048 grams of hydrogen in my 1 mole of benzoic acid. And last, oxygen. I have 2 moles of oxygen times the 15.9994 grams of oxygen in each mole. And that gives me 31.9988 grams of oxygen in my 1 mole of benzoic acid. I would simply add all of that up, and 122.1238 grams is my mass of 1 mole of benzoic acid. I have to recognize that the molar masses in the periodic table are based on measurements. So that means each molar mass has a precision. To get the precision of my molar mass of benzoic acid, I have to reflect the precision of my inputs. And I find that my inputs for carbon and hydrogen stop at thousandths of a gram, while my oxygen input has a little bit more precision. So I need to cut off after the thousandths place. So my final answer for molar mass of benzoic acid is 122.124 grams per mole, 6 significant figures. Let's go ahead then to use this information I just calculated for benzoic acid to figure out how many moles are present when I know the mass of a sample. So let's say I weigh a mass of benzoic acid. That benzoic acid weighs 68.3 grams, and I want to know how many moles are present in that sample. Now I'm going to start with the grams. I want to convert that to moles. So to do that, I need the molar mass of benzoic acid. We already calculated that from the previous slide. I know it's 122.124 grams in each mole of benzoic acid. So the way I will use this information is to turn this equality into conversion factors. Now, since 1 mole equals 122.124 grams, I can create two possible conversion factors. I can put grams over moles or moles over grams, and each one of those is equivalent. Since the top and the bottom of those conversion factors are equal, actually my conversion factor is simply 1. So I can multiply anything by that and get the right answer. This is always going to be true in a conversion problem. So as I do with any conversion problem, I'm going to start with my information that I have, show the number or the final answer that I want, which is in moles, and then I would multiply that by some kind of conversion factor here. The conversion factor I want to use will cancel grams and keep moles. So if I look at my choices above, the appropriate conversion factor for this problem will be this one. That has grams in the denominator, moles in the numerator. So I plug that in, then I simply do the division. So let's do that on our calculator. Move the calculator over here where we can see what we're doing. So 68.3 divided by 122.124 equals, and you can see I get a huge number of digits. So 0.55926766763. So let's write that in here. Get rid of my calculator. That's what my calculator gives me. And there's even more digits beyond that. But again, I start out with only 3 significant figures of information in my input, which means I need to round my output to that same number of sig figs. I need to cut off here. And after I do that, I round to 0.559 moles. Okay, there's a conversion from mass to moles. Let's go the other way. Let's assume that I have knowledge of how many moles of benzoic acid I have. So let's start there. Let's say I have a sample that contains 1.882 moles, and I want to find out how many grams are present in that sample. Well, I need the same information. I need the molar mass of benzoic acid. We already know that. I have 122.124 grams in each mole, and I can represent that as an equality. 1 mole of benzoic acid equals 122.124 grams. Same two possible conversion factors, grams over moles or moles over grams. I'll always, as I do in every conversion factor problem, start with my input, write down the desired output, and then multiply by some kind of conversion factor that will get me there. Now in this case, I want to cancel moles and keep grams. So the appropriate conversion factor is that one. Let's plug that in. Grams on top, moles on the bottom. Let's go back to our calculator. This time I take 1.882. I want to multiply by 122.124 equals, again, some very long number of digits. I have 229.837368. Let's get rid of my calculator. We'll put that in. Now I have to go back to my inputs and figure out what's limiting my sig figs. For my starting information, I have 4 sig figs here. From my conversion factor, I have 6 sig figs in that numerator. Remember, the 1 mole is a definition, so that won't limit my sig figs. So I have to cut off at 4 significant figures, which means I cut off right here. So when I round that, my final answer is 229.8 grams in that 1.882 mole sample of benzoic acid to 4 sig figs. The last thing we're going to look at is to extend our calculation into a multi-step problem where we're trying to calculate the number of atoms in the particular sample that we're dealing with. In this case, we're going to try to calculate the number of carbon atoms in a 12.9 picogram, or pg, sample of benzoic acid. Now in this case, a simple conversion from mass to moles isn't going to be enough. First of all, we don't have our sample mass expressed in grams. It's expressed in picograms. And remember, pico is one of the prefixes. It means 10 to the minus 12. So the first thing I need to do is to convert my picograms into grams. Then I can convert into moles of benzoic acid, but I can't stop there. What I'm interested in is how many carbon atoms there are, so I need to figure out then how many moles of carbon are in that benzoic acid, and lastly, convert that to the number of carbon atoms. So this is a four-step conversion factor problem, and it always helps to write out the steps that I intend to take, and then I can apply the appropriate conversion factors in sequence. So of course I'm going to need the molar mass of benzoic acid, so let's go back to this, same place we've been before. Then I'm going to need a conversion factor between picograms and grams. To do that, I can take advantage of my definition of a picogram, which is 1 times 10 to the minus 12 grams. Two possible conversion factors then are 1 picogram over 1 times 10 to the minus 12 grams, or 1 times 10 to the minus 12 grams over 1 picogram. And I can select that at the appropriate time. So let's start off our problem. Here's our starting information. My first step is to convert those picograms into grams. So let's apply that definition. The conversion factor I'm going to need comes from that first set there. So my two possibilities are here. What I want to do is cancel picograms and keep grams. So I'm going to use this one. And I notice when I do that, then picograms does cancel picograms here. And were I to stop the calculation there, I would have the grams of benzoic acid. So I'm ready then to take the next step to go from grams to moles. Now I need to apply one of these two conversion factors. I want to cancel grams and keep moles. So the one I'm going to choose will be that one. When I do that, then grams cancels grams. So that's exactly what I want. If I were to stop there, I would have the moles of benzoic acid, but I'm not ready to stop there. What I'm interested in is the number of carbon atoms, meaning my next step is to convert moles of benzoic acid into moles of carbon. Now I can get that relationship by simply looking at the formula. Notice that there's 7 carbon atoms in each molecule of benzoic acid, meaning there's 7 moles of carbon in 1 mole of benzoic acid. There's that equality, which means there's 2 conversion factors possible this time. I can have 7 moles of carbon over 1 mole of benzoic acid, or the opposite, 1 mole of benzoic acid over 7 moles of carbon. I want to cancel in my formula here, I want to cancel moles of benzoic acid and keep moles of carbon. So the conversion factor I'm going to select will be this one. And then I can cancel moles of benzoic acid, top and bottom. And if I were to stop there, I would know how many moles of carbon atoms I have in my sample. But of course, I don't want to stop there. I want to take the next step, which is to go from the moles of carbon atoms to actually how many atoms are present. And for that, I'm going to take advantage of Avogadro's constant. 6.022 times 10 to the 23rd atoms in that mole of carbon gives me 2 possible conversion factors, 1 mole of carbon over 6.022 times 10 to the 23rd atoms, or 6.022 times 10 to the 23rd atoms over 1 mole. What I want to do is to cancel moles of carbon and keep atoms, so I'm going to use this one. So my last step then is to apply the conversion factor this way. Moles will cancel moles. And I'm left with the units I want, which is atoms. So that's the setup. The hard part is done. The last thing to do is then to complete the calculation. I'm going to do that. So the first thing I input is 12.9. There's my 12.9. I'm going to multiply that by 1 EE12, and I need minus, so there's that. The next step will be to divide by 122.124. So divide by 122.124. The next step then will be to multiply by 7. So let's do that. And my last step will be to multiply by 6.022 times 10 to the 23rd. So multiply 6.022 EE23 equals, and now what I get is a very long number. I'm going to put that in scientific notation. So 4.45274145758, etc. So I'll keep an appropriate number of those digits, write that down here. So here's my final answer my calculator gave me. Truncated a little bit, 4.45274148 times 10 to the 11th carbon atoms. Now I have to round that. And to do that, I have to go back and look at each of my steps in my calculation and see which is limiting my significant figures. Well, look at my starting information. I have 3 sig figs here. And then my next step, the molar mass of benzoic acid, that's a measurement. So that gives me 6 significant figures from there. So if we go back and enter that in, so 3 sig figs here, 6 sig figs there. My next step, which is this one, now that's a ratio of 2 whole numbers. And whenever I'm using whole numbers, those are not going to affect significant figures, so I can ignore that part. My last step, invoking Avogadro's constant, I've expressed Avogadro's constant to 4 significant figures. So it turns out my limitation then is the 3 significant figures from my input. 3 sig figs here. So I need to round my final answer to 3 significant figures. And when I do that, I would cut off right there. And I would end up with 4.45 times 10 to the 11th atoms of carbon expressed to 3 sig figs.